Showtime. Welcome to Chill Skills, Sporlan Tech Talks. The topic for this session is supermarket high side components, head pressure control valves. This is the second in a series of presentations that will follow the agenda of the old supermarket seminars. In the past, Sporlan had a team of professionals on a supermarket team that went around the country to facilitate these presentations. With this additional Tech Talk entry, we are continuing to bring the supermarket seminar concept back and hopefully servicing a bigger audience in the process. Now, just so that you know, we've got an upcoming Sporlan webinar here in the month of January, actually on the 15th of 2020. It's going to cover liquid line components, catch-all filter dryers. It's an exciting, riveting presentation that will have some brilliant guys doing the presentation, and you'll learn a lot if you happen to sign in and listen to that. Hopefully you will do that. Now, there's a few ground rules for you to note. When joining the webinar via Zoom, if you do not have sound via your computer, you can always dial in with, I think that would require the use of a phone. Please mute your microphone. We don't want to hear anything you want to say. We only want you to hear what I have to say. Type your questions in the question and answer window. If it's pertinent to the conversation, we'll try to answer it live. When joining the webinar via Facebook Live, type your questions in the comments section. And just so that you know, this webinar will be recorded, and we'll re-record it until we get it right. Watch it again on Sporlan's YouTube channel, Sporlan Video. Now look at these two good-looking devils. Ordinarily, you'd have two presentators, Jim Eckelkamp and Jim Jansen. I guess that's presenters as opposed to presentators. Mr. Eckelkamp has seen fit to go into retirement. He's had enough of this stuff and has had too much fun, and he's moved on and is going to do other things. So you're stuck just with me. I'm Jim Jansen. I'm a senior application engineer here on the application team in Washington, Missouri. If you have any follow-up questions or feedback, you can contact us via email. You see my email address up there. You can always go direct to the Sporlan Tech Support team at svdtechsupport@parker.com. Or if all else fails, you can call 636-239-1111, and one of our humans will answer the phone and answer questions for you. Pretty novel concept there, huh? Now, here we've got a basic refrigeration cycle depicted schematically. This has the four main components. We'll highlight them a little bit here with a little bit of animation and circle them. Four components: the compressor, which provides the low pressure, low temp vapor and increases its pressure so that we're able to have the phase change that ultimately allows us to then go through the condenser and condense the refrigerant and create a liquid. It works in conjunction with an evaporator, which is the low pressure, low temperature heat transfer mechanism. It allows us to transfer heat from that spot that we're trying to cool or refrigerate. There's also a metering device. I'll point that out here with my cursor, my mouse. Here we've depicted a thermostatic expansion valve. And it need not be a TEV per se. It could be any of a number of different devices ranging from automatic expansion valves to fixed tube orifices or even a capillary tube. But every vapor compression refrigeration cycle has these primary components. Now, here's an actual rack. This is a system that is actually in our engineering lab here in Washington, Missouri. The modern refrigeration system is fairly advanced and can seem very complicated, but the thing to keep in mind, they always have those four basic components that I discussed prior to this slide. Some installations have multiple and distributed racks throughout the store, if we're talking about a supermarket. Other designs include one or more compressor racks in a mechanical room with split suctions intended to satisfy both low and medium temp refrigerated cases. And these systems may include different refrigerants, condenser types, unloading devices, subcoolers, heat reclaim, head pressure control. Here you can see compressors, control panels, an oil separator, oil reservoir, oil filter, oil level controls, and even examples of our Y1236 differential valves. And it's just like any other basic system. The more components you add, the more complicated it looks. But if you break it down into subsections, you can make good sense of it. And that's what we're going to do here. We've got the whole system in a diagram schematically right in front of you. We're not going to try to talk about the whole thing all at once. We're going to only talk about a portion of it. Over time, we'll review the entire system and we'll discuss the controls associated with each one of those four main system components. But right now, we're going to begin with the compressor outlet and move right on over to high side components and discuss head pressure control. Just as a refresher for you, the last time we began with the compressor and we moved on over into the heat reclaim and split condenser valves. We're moving a little further down the system, and eventually we're going to make our way completely around it. Factors affecting condenser capacity. This is a little bit of a review. There's some basic things that really play a big part in this. Temperature differential. And that's the difference between the air temp and the saturated condensing temperature, our saturation temperature of the refrigerant in the condenser. As this so-called TD increases, the condenser capacity will increase, and TD is going to increase as the ambient falls. Airflow. Variable frequency drives and fan cycle switches are used to decrease airflow and optimize condenser efficiency when we get into the off-seasonal times. You know, the more airflow across an air-cooled condenser, the more efficient it becomes. And it can get to a point where maybe we're rejecting too much heat and causing too big a reduction in the condensing pressure. Coil size. There are things like split condenser arrangements and split condenser valves. We talked about some of that last time. And holdback valves, which we're going to talk about this time, can change the condenser's effective surface area and help us control head pressure. Now, why have head pressure controls? Well, we need to maintain condenser liquid pressure to ensure that we've got adequate refrigerant feeding the expansion valve, whatever metering device we might have that's providing refrigerant to the evaporator. And we also want to ensure that compressors are not damaged from reduced compression ratios. Now, there are combinations of ways to get this done. Airside controls do a fine job. Airside options work real well down to around a 50-degree ambient temperature. And that can include things like fan control, louvers, and dampers. Once you get down into ambience below that, and especially when you get to a point where water freezes, the refrigerant side option really comes into play and does a good job. And with that, that would include things like splitting the condenser and flooding the condenser. Again, we talked about split condenser the last time we discussed this, that we had a webinar, and we're going to move on into the flooded type controls during the course of this. So that's our subject here for the bulk of this webinar. System condensing pressure, head pressure, is directly related to ambient temperature. As the ambient temperature falls, so will the head pressure in the system. At a certain point, head pressure will approach the suction pressure. Well, if you shut the system down, it will for sure eventually, but we're talking about those instances where we're trying to keep the system up and operational, much like what you'd see in a standard supermarket situation. They've got to run 7 days a week, 24 hours a day, every day of the year to keep food and products fresh. Pressure drop across the TV can reduce to a point where it can no longer feed refrigerant if we don't take measures to control the head pressure on the system. Approximately 50 psi differential is the kind of the limit for most thermostatic expansion valves. Case temperature will suffer if we don't maintain head pressure control. Scroll compressors need a minimum pressure differential to maintain engagement of the scroll sets. One particular manufacturer with axial compliance, they use that to maintain the tip seal. Low differential pressures across reciprocating compressors can damage reed valves due to flow rates and density issues. Sounds like stuff that we ought to talk about a little bit here. Below a 2-to-1 compression ratio, you're trending on thin refrigerant there. Airside control, cycling fans, modulating fan speed, 2-speed motors in the old days, variable frequency drives today, louvers and dampers. These contraptions can possibly be fouled with ice in the wintertime. That's why on the refrigerant side control, flooding refrigerant into the condenser allows us to maintain good high side control and operation. If the ambient temperature falls, so will the head pressure. To maintain flow of refrigerant and protect the compressor, the condenser and liquid pressure must remain near the design conditions. At what I was talking about a little bit before, at low compression, I have to untie my tongue, compression ratios, reed valves can actually flutter and subsequently fail in fatigue, which basically that's a compressor change that you might have to undertake. We don't want to avoid those sorts of things. Here we have a diagram which displays one way of flooding the condenser and controlling high side pressure, head pressure, if you will. It's a simple schematic. We've got 2 valves. This results in an adjustable combination. This is the ORI and the ORD, 2 Sporlan valves. Their name tends to infer what they do. The ORI opens on a rise of inlet. The ORD opens on a rise of differential. 2 valves, which are used to both flood the condenser while maintaining a flow of refrigerant to the receiver, and thus keeping the expansion valve fed and maintaining system operation. This adjustable combination you might see in a walk-in cooler or remote condensing unit. The ORI in the drop leg responds to pressure at the outlet of the condenser, opens on a rise of inlet conditions. Now, just a cautionary note, this particular valve, the ORI, is built with a flexible bellows arrangement. I'll show you a cutaway of this valve here in a slide or two. It's not suitable for use on R410A nor on CO2 applications. Just so that you know, as the pressure falls below the valve setting, the ORI, it modulates, backs up refrigerant in the condenser while increasing the condenser pressure. This in turn helps to maintain receiver pressure. The ORD opens on rise of differential, maintains receiver pressure at or above the minimum design pressure. It pressurizes the receiver with discharge gas. Here's that cutaway I was promising you. This is the ORI. Here's that flexible bellows arrangement. In order to be very responsive, there's some amount of flexibility that is inherent, and you can't have everything that you want. You can't have that good responsiveness and flexibility and have the most durable strength in order to handle the elevated pressures of 410A and CO2. So this valve, while suitable for most HFC applications, would not be a good choice for that. Now there is we said it was adjustable. Up here, if you remove this cap, you access an adjustment mechanism. You can adjust the cap with an Allen wrench. Just talking about failure mode, that bellows is the potential weak point with a bellows failure, not hold setting. Something also to keep in mind in days gone by, as depicted here, Sporlan painted these valves in the past with Battleship Gray. We actually got a deal on surplus military paint in the old days. And we painted everything with that color. I mean, office furniture, desk, file cabinets, walls. Heck, if you sat in your desk, behind your desk too long, you might get painted gray. In more modern times, you'll see most of these products as depicted here with this ORD. They will be unpainted. We've continued to improve our ability to braze and have a good looking joint. It was really purely a cosmetic issue. So most everything that you'll see that has been painted in the past, if it was brass or copper, you're going to see it in an unpainted state these days. Here we have a cutaway of the ORD. That's an open on a rise differential. Now, this is a valve that cracks open, helps keep the downstream side fed with refrigerant, so things like the expansion valve can continue to feed. And this valve's not adjustable, and that's why we make versions with different settings. They're available with 20, 25, 30, and 35 pressure PSI differential modes, and it requires about a 6 PSI reduction in differential to close it. Now, if there's no differential across the valve during like normal operation in June, July, August in the northern hemisphere of the world, that valve's going to be closed. We want the refrigerant all going through the condenser and taking advantage of the entire capacity of the condenser to do its job. As we begin to back refrigerant up into the condenser, the need to be able to bypass increases. And once we get past that 6 PSI differential, the resistance due to an internal friction sleeve starts to be overcome. And once we hit the 14 PSI differential point on the standard ORD with a 20 PSI setting, we start to crack it open. So that by the time we reach the 20 PSI differential mark, we're at set point. That's the rated position for this valve. And it's certainly partially open. And by the time we add another 10 PSI on top of that, we're at full rated stroke. Now, what I just described accounts for the operation of an OROA and the ORD4-20. They both operate very similarly. In fact, the OROA, which we haven't discussed in great detail yet, actually has an ORD as part of its mechanism. And that's what we're going to discuss now. The OROA is a combination of the features and functionality of an ORI, and that it opens on a rise, but it opens on a rise outlet. But it also has an ORD as an integral part of the assembly. The ORD is actually built into the discharge inlet and responds to differential pressure and bypasses gas to pressurize the receiver. The OROA responds to outlet pressure and stacks liquid, flooding the condenser when receiver pressure falls. Now, this valve is not adjustable. There's 3 connections to make in the system. We've got standard settings built into it. It's actually charged to a setting when we produce the valve in the factory, in the manufacturing environment. Some typical settings are 100, 180, and 210 PSIG. We've even done custom settings for OEMs over the years when the need arose. And like the ORI, this valve's not suitable for use with 410A nor with CO2. This is yet another option that we have to help our customers with head pressure control. This is the low ambient control, the LAC. We make an LAC 4, 5, and 10. Again, LAC acronym stands for low ambient control. Most of you will refer to these head pressure controls as headmasters. Now, headmaster is a common term for the product that was coined by one of our major competitors years ago. And headmaster, it's kind of a funny term, and it sounds like the principal at a boarding school, but that was the common name used throughout the industry to refer to mechanical regulator that helped provide head pressure control. And it's a common term. And this particular product is the one that most emulates the old headmaster's functionality. Now, we've got 2 different types. The LAC4 responds to changes in discharge pressure. It has some peculiarities in the way it's made internally that allows that to function that way. The LAC 5 and 10 are nearly identical internally. There's a passageway that connects the discharge line, or the connection to the receiver actually, to the underside of the diaphragm assembly, and allows it to respond to that. But they all stack liquid, flooding the condenser and ultimately pressurizing the receiver. Now, one thing that I haven't mentioned is this use of a check valve. The LAC 4, 5, and 10, because of the way they're manufactured, always have a passageway that would potentially be open from the receiver back to the condenser. So let's say you're in an off-cycle situation, it's cold outdoors, the condenser's nice and cool. Refrigerant could hypothetically or theoretically migrate from the receiver back to the condenser, causing all kinds of trouble when you go into a startup mode. The check valve here in this leg will help prevent that. Now, you could say, well, why don't you have a check valve with the OROA or the ORI ORD combination? Well, if you want to buy a check valve and put it in, knock yourself out. This particular valve, the LAC, really requires it. The OROA will tend to close off and prevent that. The ORI will tend to close off and prevent that. So if you want a check valve in either one of those instances, you can certainly do it, but with the LAC, you really do need it. Just a couple troubleshooting tips. No refrigerant at the TEVs. As long as the ORD portion of an OROA is functioning properly, you should have adequate refrigerant at the inlet of an expansion valve, but possible low charge. High condenser pressure, might have an undersized receiver during the summer months. And that's something to keep in mind if you're going to deploy this refrigerant side head pressure control technique with valves. The use of a receiver is absolutely required. The use of an appropriately sized receiver is absolutely required. Sometimes when our tech support group gets a call, they'll go through all the troubleshooting. A customer may have just installed valve side head pressure control, and lo and behold, we may come to the conclusion that the receiver is not large enough. Oftentimes when we get to that point, we learn that, well, not only is it not large enough, but there's not a receiver in the system at all. So that's one of those things we need to make sure that you size the receiver appropriately. Things like a dirty condenser or blocked condenser airflow can result in high condenser pressure, high side pressure. A possible cracked diaphragm might indicate that you need to replace a valve. And we have a bulletin that really deals with all this. It's bulletin 90-31. You can find that on our website. In fact, you can download any of our literature from our website. You've got ready access to it if you got an internet connection. The OROA and LAC troubleshooting. If you're constantly bypassing discharge gas, you may have exceeded, with the natural geometry and piping arrangement of the system, you might have exceeded the ability of the OROA or the ORD to remain closed during normal operation. Or there might be debris in the port. Now, debris is an ornery animal. Debris and foreign matter in a vapor compression refrigeration cycle can cause all kinds of havoc. And we're going to talk about that during our next webinar. We're going to talk about the removal of contaminants and how to keep that under control. If you happen to overheat the valve during installation, it's a good likelihood that you're going to have a malfunction, which will be typified by bypassing gas when you really don't want to do so. There's other times when that can happen as well. Now, here's a bulletin 90-30-1. Again, you can go to our website and download this. If you're going to back refrigerant up into the condenser with the intent of helping to control head pressure during the off-season times of the year, that means you've got the refrigerant in the system that you're able to back up into the condenser. That means you got to add that refrigerant. And there's a fair amount of calculations that you need to go through and good practice in order to determine how much extra refrigerant that you're going to add so that can happen. And that's where the receiver comes into play, because it's got to go someplace in the summer. And the extra refrigerant charge and the receiver size are both extremely critical components. So you can refer to this bulletin right here, 90-30-1, for some guidance on calculating the extra refrigerant. Once you have the extra refrigerant, you know how much needs to be added, then you can determine what the receiver side is going to be. Now, there was an old rule of thumb that I'm one of those old timers, that some of the old timers used, and that is you just simply double the normal refrigerant charge that's already in the system. Well, I'm not going to say that doesn't work. And just as soon as I do, there will be somebody that takes me to task and proves me wrong. What I am going to say, if you're going to go down this path and use this technique, use every available tool at your disposal to do a good job of determining what you're going to add as far as extra refrigerant. In fact, it'd be a good idea to even touch base with the manufacturer, because they may have all of that worked out for you. The OEM may have already determined that you need a certain combination of valves and that you need a certain amount of refrigerant if you're going to do this. So that is one thing that's probably in your best interest to do right off the bat. Barring that, we've got lots of charts and tables within that bulletin that will help guide you towards determining the amount of this additional refrigerant. The condenser volume and the volume of the associated piping as well must be calculated if you don't have any other information from the equipment manufacturer. And so these charts can assist you with that process. Now, for the ever more popular microchannel condensers, again, I'm going to sound like I'm repeating myself, probably best to consult the manufacturer for those details. Then, based upon the minimum ambient temperature, the percentage of the condenser to be flooded can be determined. Repairing system leaks. Now, this is important to bring this up for a number of reasons. And it comes into play, especially with respect to, we're talking about receivers and extra refrigerant. In the event of a system leak, we always are going to say one of the primary things that you need to keep in mind is that the need for contamination and the management of that. And one way to do that is with the installation of an appropriate filter dryer. Of course, we're always going to recommend the catch-all. And then once that's been done and the leak is curtailed, charging in order to clear the C-all, the moisture liquid indicator, would be one of the next steps. Now, there are some systems that are designed to operate that don't necessarily require a clear sight glass to function properly. That's based on the manufacturer's recommendations. I'm not going to argue with that. But barring that, a clear C-all or sight glass is a good next step. Calculating the amount of refrigerant to fill the condenser and determining the percentage of condenser to be flooded at minimum ambient, and making sure the receiver is large enough. Usually you don't want to exceed the 80% mark on that. Add the extra charge. Depending upon the ambient temperature, the valve side head pressure control, the Ori A in this particular case may be engaged in stacking up liquid in the condenser. And again, use that bulletin 90-30-1. Now, in this diagram, we are depicting industrial versions of valves that could be used for head pressure control. And we're depicting the Flowcon series A8 and A9. Those are manufactured by our sister division. And these are industrial components. We are planning on having a future webinar where we're going to detail the Flowcon product, both for head pressure control, hot gas bypass, evaporator pressure regulation, whole works. This particular instance, I'm showing these valves to you to depict that we do have adjustable valves that get into the industrial range of components. They occupy the traditional spots that you might see occupied by an ORI and an ORD. They are adjustable. And this is depicting an instance where you might have both air side modulation and valve side refrigerant control working hand in hand. The sequence of events would go something towards the fact that you might have the three-way valve, which is depicted off there to the left, engaged and functioning properly. Condenser fans could be then cycled and staged, and then the A8 and A9 would come into play. Over here, There are typical fan settings that are depicted that work in conjunction with the settings on the A8 and A9. And you can see that during normal, say, summertime operation, the entire bank of fans could be functioning. And you would eventually stage fans down to the final bank of 2 or even 1 fan that may even have a variable frequency drive attached to it. That split condenser valve to minimize the surface area of the coil by deactivating the summer condenser. And then you'd finish staging the fans again down to that final 1. In some instances, all fans will be cycled off before engaging the holdback valve and flooding the condenser. Flood the remaining condenser to deactivate the coil, and with the A8 if the pressure reaches, as depicted here, 165 psig, and maintain the receiver pressure with the A9. Now, we haven't really talked about the A8 and A9. These are going to be detailed in a future presentation. Now, what we've done here is substituted the ORI and the ORD in place of the A8 and the A9. Now, keep in mind, the ORI and the ORD are essentially the valves we talked about before, and typically these valves may very likely have inadequate capacity to handle large commercial or industrial size loads. That's where the A8 and the A9 would come into play. But we're just depicting it here just so that you get a feel for the functionality of all these valves. Now, here's a little trick a lot of people don't know. Over our history, we've only made one size of ORD. The 4 is a relative term that indicates the port diameter. And we've only got one size. While they're fitted with different springs so that they can have different settings as far as the flow is concerned, we only have the one. However, if you were to install ORDs in parallel, in fact, I'll say a generalized statement, Sporlan head pressure control valves may be applied in parallel to provide higher refrigerant flow rates for large systems with load requirements greater than any single valve's capacity. So I've seen instances where there are 2, 3, and even more ORD4s in parallel. Maybe a good indication for a reason to make a bigger one, but we never did. Likewise, if you get into a situation where the setting of the valve is inadequate and you don't have ready access to one that will work in your system and you want to prevent it from bypassing all the time, you can stack them up in series, and that spring rating is additive and it increases the setting. 2 good tricks to know. And while these techniques are probably best applied to ORDs, in theory, they could be applied to other Sporlan head pressure control. Well, here's that same system again. What have we got going on here? Well, we've got some electronic controls in conjunction with electrically actuated valves. Here you see one of our traditional step motor valves occupying the spot that an ORA or an LAC would have had. Kind of a neat thing. It's working in conjunction with an ORD. Now, that's to say, if there is a reason and a need and it makes good sense to have this type of control in place of a mechanical regulator, as long as we are willing to install the appropriate electronic control, which gets feedback from the likes of pressure transducers, then sends the appropriate signal to the step motor valve and tells it what to do, we're in Fat City. And you can use this as a holdback valve in conjunction with an ORD to pressurize the receiver. And the neat thing about this valve is certainly adequate to work in conjunction with 410A applications. From an electrically actuated step motor perspective, CDS valves, which are shown here on the left, are approved for liquid holdback. SDRs, which is a discharge regulator, and the CDS valve are approved for receiver pressurization applications. Here we've got the Kelvin 2 pressure control, which sends a signal to the valve and tells it what to do. And we've got a wide range of pressure transducers available to help tell the Kelvin controller how to manage the valve. Pressure control is a standalone controller that can communicate to most EMS systems via something called Modbus, and Modbus is just a serial communication protocol developed for these kinds of applications. Been around for a long time. I sometimes think I have been too. Now, we're just about to wrap this up. Sporlan.com is a good resource for you to use. We got technical support, product literature, training. We got our e-newsletter. You can sign up for that. We got product videos, events. We've got even occasionally release the new product. I say occasionally, I'm being facetious there. Virtual Engineer, we got our new sizing and selection tool out there. You can stay connected with us through a blog, Facebook, Twitter, our Sporlan YouTube channel. Again, we've recorded this webinar and it will be posted on Facebook Live and on our YouTube channel. You can always reach out to Sporlan Technical Support. Phone number 636-239-1111. We've got an email, svdtechsupport@parker.com. Every once in a great moon, I'll answer emails. Every once in a while, I'll even be the one that answers a phone call. But we've got folks that are dedicated to that. We've got folks that have years of experience with us who are skilled at helping you to get answers to your problems. Ordinarily, we handle questions at this point in time. We're going to move on through that. And just to remind you that we've got an upcoming Sporlan webinar, January the 15th. We're going to talk about managing contaminants in a system and how to get them out. From our perspective, there's two things that should be circulated through a vapor compression refrigeration cycle. One is refrigerant, one is lubricant. Everything else, as far as we're concerned, is a contaminant, and we've got ways to get it out. So you can sign in and listen to that webinar and learn all about that. Thank you for joining us. Have a nice day. Go back and listen to this again at your heart's content and join us for the next one. Thanks.